So I've been asked to give this talk in English, so I'll continue in English from now on. I hope that's fine for everyone who joined us today. So this is Symbolic execution for security researchers. I'm Arnau. I do things at places you have listed there. Also important, if you just wanna go through these slides before and go back and forth, you can just scan this QR code. This will give you the same slides that are being displayed here for you already, okay? So while you scan that, if you want, well, as I said, I do math and hacking for a number of places. I work as a fancy title security at Activision, do trainings and other kind of research at Fura Labs, which is kind of my own security firm. And also I'm doing my PhD remote, but officially at the University of London. And you can reach me. I'm sure you can find me around in the internet, but anyway, this is my website where you can find links to every place I'm around. So what is this about? A little bit of preliminary for the content that we will be displaying. So what are the expectations for the talk? It aims to be pretty introductory, so it's not, while it's technical, it won't go very deep into any of the subjects. The main idea is to demystify what is symbolic execution for a non-specialized audience, so you can get the idea other than the tooling or specific tooling or very specific use cases. I just want you to get the idea on how you can use that to your own needs or to your own scenarios that you can face on your daily needs. Also, maybe, probably, hopefully, making it easier for you to contribute to other tools, build your own tooling, and, well, see what's beyond usual analysis or usual reverse engineering techniques. This can help you in a number of scenarios. So what is a calculator? Let me start with that. A calculator, or if you want a computer in a way, is something that does concrete calculations. And by concrete, I mean I provide some specific inputs, some actual values, and I produce a concrete output, a concrete calculation. In this case, I just take this random example, which is, well, a determinant of some matrix, and this is the actual calculation of the determinant of this matrix. This is what a calculator does, calculates things. And I want to make the comparison with what is usually called a computer algebra system, which has a very fancy name, but the only thing that it does is let's try to plug into a computer a way of reasoning about math or code, if we want, that deals with parameterized inputs. That's what you do by hand when you have to solve some equation, where you have to work through some system that has some unknowns. Well, you have to work with things that you don't know beforehand, so you cannot compute an actual calculation, a concrete output. You have to carry on, in a way, the symbol or some of the symbols, so you can then reason about that. In this case, we have, again, a determinant of a matrix, and what is the result of that? We don't have an actual result. We have a result which is parameterized, which depends on one of the inputs that has a symbol, in this case A, which we don't know. And then we can do things about that. We can say, okay, what is the value for A? So this determinant is greater than 0, negative, lower than 100, whatever. We can reason about that. So with that in mind, okay. Another thing that I want to present are intermediate representations and intermediate languages. We won't deal with that in general, but I will mention a couple of times, so I want you to know what I'm referring to. Essentially, an IR and IL is just a language that is abstract and helps in analysis of computer programs in general. And you have worked with that, even if you don't know. Anytime you hit the decompiler on any disassembler, it goes through an intermediate representation process, or every time you compile something, either with GCC, with Clang, or with your favorite compiler, it goes through an intermediate representation. And those intermediate representations then allow to apply optimizations, both on the compilation or the decompilation part, that are generic on the architecture, on the target architecture, okay? So they're very used in the industry for analysis, to be able to do architecture-independent analysis in a way, both from the compilation, building process, LLVM IR is a very famous one, but also from the decompilation one. Every time, for example, in IDA Pro that you hit a decompiler, you don't get from binary to the pseudo-C. There is a microcode intermediate representation happening in behind, and actually you can explore that with the help of some plugins if you're interested. Here you have, okay, yes. So what is actually symbolic execution now that we have said some of the preliminaries? Well, it's just a computer algebra system, thing that we just saw, which is the idea of being able to reason about the computations, the calculations that are happening with respect to some unknown values that we will just put some symbols, carry them on, and then at some point decide, okay, what this value needs to be in order for me to reach my target, whatever that target might be. We can have this symbolic execution, target different languages. They can be just programming languages. We have symbolic execution engines for C, for C++, for Java, for Rust, for your favorite language. You can have symbolic execution directly built on top of assembly languages or your favorite architecture, and also on top of intermediate languages. That has a number of advantages. Namely, you can just build your analysis, your tooling on top of an intermediate representation, and then when you want to support some new architecture, the only thing you have to do is translate or lift, as it's usually called, from your native architecture to your intermediate representation, and then you have all your tooling and all your analysis for free already. But more specifically, symbolic execution is a program analysis technique, which means this is a technique that allows us to analyze programs, to do program analysis, which can be binary analysis, but not necessarily binary, okay? For the most part, I'm interested in binary analysis, but it's something that works in general. So the basic idea is, as with a computer algebra system, we represent some inputs as symbolic variables instead of concrete values, so we give them some names that we will carry on. And then we derive some constraints to encode control flow and data flow with respect to the symbolic values, okay? What does that mean, deriving constraints? Deriving constraints means deriving conditions. So we have some values for some input parameters, and then we derive, okay, what is the condition that these two parameters have to satisfy so we end up at this point in the code? We'll see some examples. Let's start with this one, just to illustrate that. This is a dump C function that does absolutely nothing interesting. Receives us inputs to integer parameters x and y. It does some computation on the x, and then there is some comparison. If x is less than y, then we return something. Otherwise, we return some other thing. We don't really care. So what is a concrete execution or emulation, if you want? It works the same scenario. We just, well, throw concrete values. So we just throw some actual inputs, some integers in this case, 32-bit values, and we just compute the things. So it's just, well, give the values to x and y, make the computations that are happening here, and then at the end, we see that, well, the first statement for the x puts its value to 3320, and then we check that this 3320 is less than the initial value of y, so we return the first computation. And at the end, we just return a concrete value. This is a concrete execution. This is what a calculator, an emulator, or just your regular executing a binary does on any function or any level of the code. What is the idea of symbolic execution in here? So we can see in this example in C is, well, let's just say that x and y are just symbols now. I just bolded them a little bit. So we are not giving them actual values. We're just carrying them on and see what happens. So the first thing that happens is that the first assignment says x, symbol of x, now is y minus 3x, and we're just carrying that on. So what is the first condition? The first condition says if x is less than y, but what is x now? It is y minus 3x, the symbol for original input parameter. So we have two different cases. We have the case y minus 3x is less than y, then we will compute this expression, which is exactly the expression that we have in there, but now our x, we know that it will have to be y minus 3x. But on the right, we have the other scenario in which we say, okay, but what if y minus 3x is greater or equal than y? Then we compute the other scenario. And here the idea is we might be interested in reaching a certain point in the program, or in making sure that at the end, the return value is some concrete value. Why we might be interested? Well, just a bit of spoiler, we might be targeting some branch to fast that branch, and we want some inputs that reach that branch. We will see an example about that. Or we might want to bypass some license checks, so we know that the return value for a function has to be whatever, and we want to make sure what are the constraints, what the constraints on my input, what are the conditions that my input has to satisfy so I arrive to that point that I want, so I arrive to a place that I want. And we can encode those conditions as, well, a set of constraints that we'll see. Yeah, that is very nice, but how does it actually work in real life? And have a very, very practical example here on how you go around and build a symbolic execution engine from scratch. And the basic idea is super simple. You just need two data structures, a path constraint, and a state map. The path constraint is a structure that keeps track of, okay, what are the conditions on my inputs that are required so I end up at a current instruction, at a current point in the program. So I want to be in this point in the program with respect to some inputs, okay? What are the conditions that these inputs have to satisfy so I end up at this point? Those are the conditions, the constraints that are encoded in the path constraint structure, and the state map, which the only thing that does is the mapping of the variables to their current value with respect to symbols, okay? By variables, I mean, well, if you're doing that over language, just the variables, but you can do that over assembly, usually registers and memory locations, okay? That's not important. The idea is, well, we define the structures, we, well, get into an instruction or in statement, say, okay, this is an addition of this register with that register. We update our state map, which keeps track of current symbol value. And then, well, if there's at some point some branching, because there's a jump, conditional jump or whatever, we just fork these structures. We keep track of different instances of these structures, so we can, well, decide if we go with that direction, what are the constraints that have to be satisfied? We go with that direction, what are the constraints that have to be satisfied? The state map, let me be very clear here. Why do we have two data structures? Essentially because one encodes data flow changes and the other encodes console code changes. The state map just gives us the computational process through which some variable ends up having some value at some point. So I have a return value of a function that has two inputs, x and y. And I go to the end and say, okay, what is the computational process that will provide me the return value here with respect to the inputs? And the path constraint, as I said, represents the control flow tracking. It's a way of saying, okay, what conditions have to be satisfied so I arrive to this precise point in code. So what are the conditions that have to satisfy so all the path branching over the program execution or the program control flow make it so I arrive just here where I want. I have a nice visual example that we can go around. We start with some assembly. You don't really to understand what's happening. This is completely frozen, by the way, because I'm looking right here. You guys can take a look. Okay, looks like it's going. Yeah. So let's take a visual example of what this state map and path constraint look like in real life. And the idea is we have some code in assembly. We don't care what it does. It does absolutely nothing interesting. I did that like manually just to build the example. And the idea is, well, we start with these two data structures, the path constraint and the state map. The path constraint is a set of constraints, a set of conditions, which will have at some point a Boolean value. We start with true. Why? Because we don't need any condition to be at the starting point. We just say, hey, we're starting here. We don't need any condition, so we can start wherever we want. And the state map just maps our variables in this case, which I decided to be just these three registers and zero flag, because are the only ones represented. But the state map, it would be just big to represent every single register or any kind of variable you might have, just a small example. So check that we start with moving 123 to register REX, and what happens is the state map gets updated. So now we move concrete value to REX. We just, well, update the state map. This very similar to an emulator. You have ever written an emulator. It's just that now we can keep track of symbols, not only concrete values. But now what happens, we add together REX and RSI, and see that the state map now tracks that. Now we have that REX is pointing to 123 plus RSI. We XOR REX with RTI, again, it gets updated. But check what's interesting here. We are XORing REX with RDI, but the REX that we are taking is the current REX. We don't have a concrete value. We have to go to the state map and take the current representation. Okay? Again, it's same construction as with an emulator, but we are carrying on symbolic values. And we just continue doing that. We see how the state map is getting updated. Okay? And yeah, just for that. And at some point, we are up to a jump condition. Okay? So we have at the jumping condition something very interesting. What is the value of the zero flag when you arrive at this jump condition? We had just before a comparison right here, and now the zero flag will be 1 if the comparison of REX with 137 basically if they are equal, or 0, which means the zero flag will be set to 1 or to 0 depending on the previous comparison. But we are comparing REX. What is REX at this point? From a symbolic point of view, from the point of view of carrying on the inputs that we have. Well, it's all this expression that we have in there, which is the one that has been constructed in the state map, has been updated at this point. So we just, well, give zero flag a value that can be 1 or 0 depending on the previous value. And now we have a fork. So we have a chunk, we have to fork the state. I have reduced a bit the representation here, but now we have two different states. The first state is the one where the path constraint has that all the expression that we have for REX is equal to 157, and in this case, the zero flag will be 1, and this is the case you see the arrow with the 1. That means the path constraint, in this case, means what are the conditions that have to be satisfied with respect to the inputs that are RSA and RDI in this case, so that I end up being in this particular point of code, which is the good flag. Okay? So this is the condition that has to be satisfied. And one interesting thing to note is that this condition is with respect to RSA or RDI and has nothing to do with the initial value of REX, which is the one that we have been carrying around all the time and which even has been compared. Okay? So imagine you have some inputs, RDI, RSI, and you just say, okay, with respect to the inputs, how do they arrive to this point in code? Well, if you can satisfy this equality, then you arrive to the good part. Otherwise, well, you just go to the bad, and the zero flag will be set to 0. Okay? All the time I've been saying, okay, we have to satisfy some constraints and conditions. How do we reason about that? The answer is with an SMT solver, mostly, and very small, but mostly because I won't cover anything else today. Okay? And you might guess, what the hell is an SMT solver? This guy again talking about SMTs. Basically, an SMT solver stands for satisfiably modular theories. The only thing that it means is, let's check if a formula can be true. And the modular theory is the only thing that says is, well, let's do that with general formulas, because satisfiability only works with Boolean formulas. I want to work with integers and with any kind of data type. Okay? So the SAT means, let's check if our Boolean formula can be true, can be satisfied, and the modular theories means, well, yes, but I also want to deal with other kind of data types. And from a very practical standpoint, I don't know how this works internally. It's just a magic black box that we can ask a question and get an answer. And the idea is, hey, here I have some expression on some variables. Is that satisfiable? Which is another way of saying, is there a variable assignment that will make these conditions to hold true? There are 3 possible outcomes. The first outcome is SAT, which means, yeah, sure, there is a variable assignment, and actually, when you have a SAT outcome, it will give you a solution. It's not just, yes, it's possible. No. If it says that it's possible, it will give you a concrete example of solution. We call that a model, okay? But it's essentially a solution. It can also be on SAT, or the SMT solver says, well, there is no answer. There is no valid answer. It's not possible. Or it can be unknown for a number of reasons, which usually have to do with timeouts, but we won't go into there. So, some example. Not sure if you can see that right, but it just say, let's suppose we have x and y, 8 big values, and we say the first condition is x minus 2y is equal to 100, and x or y is equal to 59. We have these 2 conditions. We ask our magic black box, which is the SMT solver, hey, can that happen? Is that satisfiable? And the SMT solver will say, oh yes, this is satisfiable. It will give us SAT, and it will give us actual model. Because if you put x 142 and y 21, then those conditions will be satisfied. Okay? That has nothing to do with if it's the only solution, the best solution, whatever best means. And we also have other examples. For example, we could ask other constraints, ask the SMT solver, and the SMT solver will say, well, no, that's not satisfied. There is no possible values for X and Y that will give you the constraints that you are looking for. How do we put that into the flow of symbolic execution? I will just give you some ideas, but basically it's imagination. But there are some very concrete use cases that are being used in the wild, I would say. One is data flow analysis, which is, well, we have a state map which is giving me every single step of the computation process. You can do a lot of things in there. The same thing that a compiler does, which are data flow optimization techniques or compiler optimization techniques. You can think of constant propagation, constant folding, reaching definitions, which is just a way of saying, okay, what are the definitions that are reaching some point? So what are the variables that are interesting for next point? Or liveness analysis that detects depth code, which is just a way of saying, okay, I'm at this point in the code, what is the code from the beginning that does absolutely nothing with respect to the computation or the output that I have here? It's just some ideas, but the thing is, as I said, the state map gets track of the data flow changes, so we can apply data flow analysis on that in the very same way, the same kind of algorithms that compiler optimization techniques perform. Kind of the most popular thing to do with that in data flow is, well, get the symbolic execution to get us the formula or the constraints for a return value function, okay? So we start on a function, and we say, okay, what will be the return value with respect to the input parameters? So give me a formula, an expression, or a set of constraints that will give me the return value with respect to the input parameters. And then just fed that into an SMT solver and ask, hey, give me some values that will return whatever I want. So the SMT can simplify that formula. If you want a nicer representation, that might be for the obfuscation uses, so SMTs are not very good for the obfuscation. We can talk about that, that's another point. Or the more useful thing is craft inputs that will make the formula evaluate to the desired output. And this is a very simple way to build like keygen for practice for free without having to reverse absolutely anything. You just go to the license verification function and say, those are my inputs. This is my output. The output has to verify the set of constraints. Give me inputs that verify that. Okay? Also for control flow analysis, we use symbolic execution to extract the formulas, the constraints, the conditions that have to be satisfied to end up at some point in the code. This is encoded in the path constraint structure. We fed that into the SMT solver, which is a way of asking, hey, what are some inputs that will make us arrive to a point in the code that we are interested in? Okay? The SMT solver can, well, essentially tell us, yes, you can arrive here, and here is some input to arrive there. And detect a few things that we will talk now in a second. Some example, if we just take the path constraint that we had before, or the good case, well, what is that? Those are 64-bit registers, so we can ask the SMT solver, hey, is this satisfiable? Is this condition satisfiable? In other words, is there any variable assignment for the 64-bit variables RDI and RSI that makes the path constraint satisfiable, that makes us being able to arrive at that place in the code? So that's what's happening. We have RDI and RSI, 64-bit values, with this constraint, in this case just one constraint, we feed that into the SMT solver, and the SMT solver will say, yeah, sure, this is satisfiable. Actually, here you have a model. If you plug RDI and RSI on the input values of your function, you will get that this equality, this constraint will be satisfied. Here is very abstract, but you can do that like in Python very easily with some SMT solver, for example, Z3, which is kind of the most popular one. This is as simple as that. Just import Z3, define your variables as 64-bit in this case, give the constraint, initialize the solver, add the constraint to the solver, ask it to check it, and if it's satisfiable, preview the model, which is the solution again, okay? And you just run this little Python code. You just run this and it will tell you, yeah, sure, this is a solution, okay? Tooling. What tools do we have to do symbolic execution? And here, It's complicated, but the answer is welcome to the jungle, basically. This slide is not for you to memorize or anything, it's just for reference. If you want to check at some point, I did that, and with the best effort intent to classify a lot of the tools that are in there, the most widely known. But yeah, so essentially we can differentiate symbolic execution tooling depending on different areas of interest. Okay, one is the technology. So how is that symbolic execution engine implemented? The most common ones are interpreter-based, and interpreter-based is what we saw in the example before. We just read the code, if it's assembly or if it's whatever, and are building those structures from the code that we are parsing, essentially. So we are interpreting the code ourselves. We also have instrumentation-based, which is, well, get a binary, instrument the binary with Intel pin, with FRIDA, with you name it, and plug this construction of the path constraint and the symbolic execution at runtime while you have instrumented all the functions. So all the structures are being generated at runtime with instrumented code. And we also have compiler-based, which essentially are forks of compilers. Cleve, SymCC are forks of Clang, essentially. And SymPimo is a weird thing we won't really cover, but essentially it's kind of compiler-based, but works with binaries. It's a bit weird. We can talk about that afterwards. And compiler-based, the only thing that they do is a fork of a compiler, is a fork of Clang that plugs all this reasoning to generate the state map, the path constraint, and the symbolic reasoning into the binary itself at the compilation process. So you have that for free when you end up generating your binary. Okay, we can also differentiate what is the target. The target can be usually binary targets or source code. For binary, we have, well, all those that you have in there. For source code, mostly Cleve and SymCC. Okay? Also, I like to differentiate them on what is the focus, so what is the intent behind the tool. The ones that I use mostly are the analysis-based, because well, those are symbolic execution engines that give you a nice API so you can build your own analysis tools. So you can construct and query the state map, the path constraint at different points in time, and you can say, okay, now jump here and symbolically execute this part, give me the path constraint back. You can essentially build your own tooling on top of an API that this gives you. Most popular ones are Miyahi, Triton, or Math, which is pretty recent, and I haven't really used that. There are also the automagic ones. You might have heard of Anger, especially if you are into CTF thingies. Redis, which is super fast and is based on Radar 2. I don't use them a lot, but they are fine if you just want quick wins. Those are the kind of symbolic execution engines where the analysis, like the usual analysis, are built for you already. So you just have to say, oh, the flag is here. I want to arrive here. Please. This is the flag. I start here. Give me input that will make me arrive to the flag. And they automatically give you that. And by automatically, what I mean is they construct the state map, they construct the path constraint, they feed those constraints to an SMT solver and give you the solutions for that. But they do that right away without you being really aware of what's happening under the hood. And also there are the test generation, which are used mostly for passing. Those are essentially, well, you throw some input, you're a branching condition, and you ask the symbolic execution engine, okay, give me a solution, give me an input that will satisfy the constraints for the left branch, and one that will satisfy the constraint for the right branch, so I can have inputs that will cover all the entire space for as much as possible, okay? And you can see that most of the analysis ones are interpreter-based, and most of the test generation ones are compiler instrumentation, but the intersection is a bit, this classification is completely mine. I mean, I made up that there are a lot more symbolic execution engines, but this is the way I ended up arranging them. Some of the most important, mostly now, okay? Okay, now let's jump into some practical applications. And just an appetizer, I will show you a couple of examples of demos of things that can be done with that and are being done, and you might be interested in knowing. One is, well, analysis of complex code, and in this case we'll see how to detect and patch opaque predicates, and what is an opaque predicate in the first place, if you didn't know. Opaque predicate is just a statement, a condition that is either true or false, and we know that a priori. Okay? The person building that condition knows that it will be always true or always false. So essentially, for example, this condition, x squared is always greater or equal than 0. We know that this is true. Okay? So if you have, for example, we can have a false one. This is not as obvious, but it's widely known because of reasons. For any x and y of the same bit size, this equality is always false. Okay? This never false. So this is a statement for which we know if it will be true or false beforehand. Okay? And why is that used, or how is that used for obfuscation? Well, you just have some code, some other code, and you put down an if or a conditional statement in the middle that says, if my statement that I know beforehand if it's true or false is true, then I will go to the rest of the code, otherwise I will go to junk code. Okay? And you're making the code more complicated to read and to analyze because you're introducing considerable diversity and more code which is absolutely whatever because it will never be reached. And the same thing for the false one. Okay? In this case, well, if it's a false opaque predicate, we just have the false branch has the rest of the code and the true branch has whatever. And we can do that iteratively, like a lot of times. And you end up with building a control flow graph for a function. So the control flow for the function will be very, very convoluted, but essentially it will be artificial complexity. Just the reverse engineering that has to do with that will have a hard time. So what is our idea for detecting and patching the opaque predicates? Well, we will just symbolically execute a basic block, which is just a unit of instructions before a branching condition, and then extract the constraints for the branching. So extract, okay, what are the conditions that will make this basic block go to the left branch or go to the right branch, or follow the true branch, and check if those constraints are always true or false. So check, hey, is it possible to have an input that goes to this branch? If it's not possible, that means that this branch cannot be reached. Okay? And if that is the case, we just patch it out. We can copy it or change the conditional jump by an unconditional jump, whatever. A visual example, I made some diagrams to see that is we start with some control flow graph. We start symbolically executing at the beginning at the blue basic block, and we say, okay, we have a branching condition that will go to the true branch, the greenish true branch, if x squared is less than 0, and we'll go to the false branch if x squared is greater or equal than 0. Okay? So in this case, we ask the SMT solver, hey, check those conditions for the path constraint of the two different branches. And I will say, well, the first one for the true branch is unsatisfiable, and the right one is satisfiable. Okay? I don't even need a model right now. So what does it mean? That the left part cannot be reached. Okay? So now those two in red cannot be reached because there is no way to arrive there. We have seen that the condition for a branching that will put us to that part of the code is unsatisfiable, cannot be reached. So we mark those as red in this case, and we keep executing, symbolically executing in the other branch, which we know that we can write. And we do exactly the same. We have another conditions, we check for them, we check both of them. Now we see that the one for the true, again, this is unsatisfiable, the one for the right is satisfiable, so we keep going. Now we have all the entire left part in here, this is completely unreachable. This is code that is there that is not possible for us to reach. We cannot reach that. There is no combination of inputs that will make us reach that code. And we can do that again and essentially see that this code in here, which also involves a loop, also is not reachable. So we end up with something like that. This control flow of a function or for a piece of code actually is just a linear piece of code which you can condense in a single basic block. This is an obfuscated version of something which is a single basic block. It's a linear flow of statements. I want to show an example, a real example of that. This technique of opaque predicates was used in external, which was a communications component of APT28. You have the MD5 in this. It's probably based on an example from a colleague team, and I will show you that. I have a video for that. Oops. No. Yes. So rather than, the only thing that I'm going to do here is get the XML, go to the function that is obfuscated, one of them, and print you a very, very, very minified version of the control flow graph of this function, okay? So here, every little star, every little dot that you see is a basic block. It's an entire basic block of instructions, okay? I just put it there because the dimension of this function is insane. And even with that, you see, this is the function, okay? This is the actual obfuscated function of the external component of an APT28. Again, every little dot, every little star is an entire basic block that can be big. Okay? Now, this goes. So now I will show you a script with miasm. I don't care, you don't understand anything in here. As I said, the target is not for you to understand totally, but just to say, hey, you just build a script. The only thing that is happening here, I initialize some stuff. I use that tree to make an auxiliary function that says, hey, give me, verify if I cannot take that branch. Okay, so there's the auxiliary function, it cannot branch, just using that tree to verify that the constraints for a branching cannot satisfy. And then I'm just initializing a lot of stuff from miasm, and at some point, the only interesting part is the one at the end, which is, hey, I'm starting at this function address, initialize some stuff, I'm loading the binary as raw as bytes. I'm traversing all the basic blocks in the basic blocks given by the assembly control flow graph, which is the graph of this function, and something. If the expression for branching of the basic block is a conditional, which means we are right at the end of the basic block that has a branching condition, then check essentially if I can take, is it possible that I cannot take the branch? And if that happens, I will just pass the branch that I cannot take. Okay? Again, you don't have to go into that code at all. The only thing interesting, check at some point that if it cannot branch from the expression to the expression source one, which is one of the branches, then, well, do some stuff and patch with knobs the part that I cannot branch. That's the whole idea. Again, you have the script, you want to check it, but it's not my intention that you want to understand that. And you understand the previous diagrams, that's perfectly fine. So again, the only thing that I'm doing is what I showed before. I'm symbolically executing every basic block. Go to the branching condition, check if the branching conditions can be satisfied. So can I go there? And if I cannot go there, I'm just knopping out that part. I'm just getting rid of that. That's the only thing that's happening here. Okay? And I will do that. Let me fast forward a little bit. We just execute that. It takes a few seconds because that function was massive, as you saw. And when it's done, which should be really soon, yes, I will show you now the control flow graph of the deobfuscated part where I remove the opaque predicates. And it's basically like that. And that is the whole function, deobfuscated. Okay? So if you're a reverse engineer and you have to deal with APT28, you will probably rather deal with that than the previous one. Okay? Now, another example with fuzzing. I don't do a lot of fuzzing, but I just wanted to include that for fun. And some other exemplification of why that can be useful. So what is code coverage in fuzzing? If some of you do vulnerability research fuzzing, you already know that, but essentially code coverage is a measure of which parts of the code of a program are already covered by the fuzzer. So we are already arriving there. And this can go into different levels. We can track subroutines called, what basic blocks have I reached, what statements have been executed. But it's just a way of saying, hey, I'm running a fuzzer, so I'm throwing random inputs, mutating them to, well, try to find bugs, hopefully on some program, on some code. And I want to know which regions of the program my inputs are reaching, because I may have some regions of the program that are completely unexplored because my inputs are not reaching that part, okay? So higher code coverage, which means, well, having more inputs that reach more places give you a higher chance of hitting interesting vulnerable code. And this is the usual example of you have some parser that has some vulnerability, but to arrive to the place in the code that has a vulnerability, you have to pass some checks on the header of the inputs that might be absolutely, like probabilistically impossible to get just by random mutating, just passing the first checks and then arriving to the interesting part of code. Okay, so we would like to increase code coverage. What is the strategy for that? How do we use symbolic execution to increase code coverage? Well, we just start our fuzzing with your target with an initial seed, initial corpus, so an initial input or set of inputs. And we use symbolic execution in this case to generate test cases, okay? And the idea is, let's take a look at the currently coverage map. Any modern fuzzer, and by modern I mean AFL, which is not modern at all, but AFL, FL++, or any fuzzer has some coverage map, which just gives you some metrics of which parts of code have been explored, okay? So symbolic execution engine will be consuming that information and say, okay, which parts of code have been already covered by the actual session of my fuzzer, and take a look at, okay, this code is not being covered. So I'm gonna go to the branching condition that would make me go to the unexplored part and take a look at what are the constraints that have to be satisfied with respect to the input so I arrive there. Generate inputs that satisfy that, feed those into the fuzzer, and now the fuzzers have some initial inputs that will reach an explored part and can start mutating those inputs to hopefully hit some vulnerable part. Again, some visual example. We start our fuzzing with some initial seed or corpus, and in the left you have the path that the current execution, just a concrete execution, we're throwing some input with the fuzzer. This is the path that this is taking, and on the right you have the coverage map. So in total, what parts of the code have we already reached, okay? So we just start throwing input, you see input 1, input 2. In this case, you see that the coverage map keeps the one that we already explored before, okay? The coverage map in the right is just, well, keeping track of the places we have already visited. And you start doing that, okay, whatever, and at some point, you have like a lot of inputs, but still, there is some part of the code which maybe has some vulnerable statements, some, well, unbounded checks and buffer overflow, whatever. But there is a really hard to reach branching, because this branching to arrive to this vulnerable code is a very convoluted constraint, a very hard condition that is not easy to trigger like by random mutation or dumb mutation, okay? So what is the idea? Well, let's use symbolic execution to generate some inputs that trigger those non-explored paths. So imagine that it's quite small, but I'm not really interested in the actual expression, and you will see that afterwards. Imagine that we have some conditions to go to branch to the places, and we represent our input as an array of bytes. So our input is an array of bytes, essentially, okay? Byte 0, byte 1, byte 2, byte 3, byte 4, whatever. So we symbolically execute the first basic block and say, okay, we want to go to that part because we want to reach the vulnerable part. We want to reach the place where we hope there is some vulnerable code, or at least it's non-explored. So we are just updating our path constraint, and we say, okay, we need to go to that branching first, so we need to update our path constraint with the condition that will make us arrive there. Now we make the same for the second one. We again update the path constraint. Again, we symbolically execute the basic block and check, okay, what is the condition that will make me go to the next block on the path that I want to build to reach my target? And the last one is apparently a super involved expression, but we want to go through that. So we just, again, get the path constraint, and we build the entire set of constraints. So this path constraint that is in there, that you will show you bigger now, is, okay, what are the conditions that have to be satisfied on my input so I end up being on the region of code, I end up hitting the region of code that I'm interested in. You just collect of the constraints that are required for you to arrive to that part of the code, ask the SMT solver, hey, is that satisfiable? He will say, yes, here you have a model. And then you can just say, okay, I'm gonna use that input. And again, you just consider that input as an array of bytes. You get that input, you feed it to the fuzzer, and well, you are now in the vulnerable code part. That doesn't mean you have triggered the vulnerability, but that does mean is that you have some inputs that will be mutated that are already hitting your target region of code that hopefully is vulnerable. So you're increasing your code coverage. You have very little time, but I just want to show you the last demo. I think I have something here. And then you just repeat. Let's try to trigger a hard-to-reach division by 0. This is a very dumb example. And the idea is, well, we want to arrive to this return, which has a division of f size minus 10. And, well, it might trigger something which is not a good idea, okay? But if you check, there is a for, which is checking a lot of different stuff and returning all the time. And then it will return also previously if the data get as an integer is not falafel, essentially. So it's very hard to reach that, to reach that part. The bug is trivial to check, but it's hard to reach that part kind of by throwing random inputs and outputs, okay? Throwing random inputs and checking what happens. So I use SymCC, which is one of the symbolic execution engines that I mentioned. And I just fork it. I made a dumb fork to make it work with AFL++ because this was an academic thing that only worked with ancient AFL. So I made a fork, I fixed a couple of things, and make that work with AFL++, newest version. And the only thing that's happening here is, well, what I mentioned. I start my fuzzer, it's going around. Let me show you. Yes. I start my fuzzer, it's going around. Well, here you have the code that you have already seen. I'm not going to stop in here. I'm going to stop here. Yes. So this is the code that I had. I just compiled with my compiler. I compiled with AFL compiler, and I compiled with SymCC. All of these three things are compiled. One is the regular compiler, other is the fuzzer compiler, other is the symbolic execution compiler. Now, I create the initial seed input, which will be Navaja Negra 2023. This will be my initial input. I will start AFL on that input. It starts doing thing. I will start a second session because I need 2 sessions for them to essentially give feedback, but that's just the gist of it. I initialize a second session. I will just spend a very, very little time checking that, well, it's not reaching that part. I mean, it's just a few seconds, but you've already seen that here you already have 50K executions. Here you already have shy of 100K execution. It's not really reaching that part. And now what we'll be executing, the SymCC fuzzing helper script that I fixed. The only thing that is happening is, well, hey, take a look at this session of AFL and generate test cases for non-explored paths. And the moment I do that, automatically I get crashes because it has generated an input that reached that branch that was very difficult to read before. And at that moment, it was very easy to mutate that and generate crashes. And if you just, well, just to show you, you just get that, get the crash, and try to throw that as input to the program, and it will just give you a floating point exception, okay? You have a crash. Yeah, so I'm basically out of time, but I will take the 2 minutes that I was still before, just to comment on limitations and some ideas to overcome some of these limitations of symbolic execution. Mostly path explosion. If you're not familiar with that, this is essentially what happens when you have a number of control flow paths that grows exponentially. So essentially, well, you want to symbolic execute something that keeps having different paths, and every time you get a path, I said you have to fork all your state. So it can very, very fast go to path explosion. Essentially, grows exponentially, okay? And you have loops where you don't have any boundaries on the, well, on the bounds of the loop or where it will stop. It can be complicated. For that, the best thing that you can do is you have to manually locate interesting code. You can just throw that to, I don't know, Microsoft Word or whatever, and just go away with that, at least not the analysis one. And also there is a thing which I haven't covered, which is concolic execution, which combines concrete and symbolic execution, and it's just, I'm gonna run my program normally, I'm gonna run a symbolic execution version that is gonna get inputs from the concrete version. So I don't have to fork the states. I just have to go at the interesting part, and at that part, I will take a look at the conditions, but not everywhere. Also, support for syscalls, for standard C library functions, and things like that. And, well, what if you have to symbolic execute something that has a call to printf? You don't want to symbolically execute all printf, okay? So as with any emulator, you just hook everything, okay? You make your own hooks and go away with that. Or if you have analysis capabilities, you just skip that if it's not interesting for you. So it's good that you have some ability to interact with the symbolic execution engine. Also, there are limits of the SMT solver. So, okay, you abstracted the constraints, but what happens if the SMT solver is not able to give you an answer? And here, this gives for another set of talks. But essentially, just to mention, you have program synthesis, which is a fancy way of saying, let's just forget about the actual syntactic representation and see what's happening under the hood from a semantic point of view. That is, throw inputs, collect output, check what is that, okay? Very, very, very broadly. You can also do math, and by math, again, we'll say nothing interesting, but I essentially mean algebraic geometry, something that doesn't ring a bell for you, it's okay. But if you are curious, we can talk about that afterwards. And imagination, okay? You just, well, try to transform those expressions to something that you can deal with. But again, program synthesis and math things work pretty nice and have worked for me for almost every single case. Also, spam, I have a training. I do things on software protection. I'll be giving next time in public in Austin in February, if you happen to be there or want to go, but also privately. We do a lot of stuff with protecting software and also analyzing things, okay? Just, if you're interested, just take a look or hit me up. And that's it. Thank you. I'm not sure we have time for the questions, but yeah, I'll be around.